Tonight's video is an introduction into exponential growth and decay. So we're going to continue our graphing. We have a couple other types of graphs we need to explore. So if you'll take out your notes packet, you are on the page entitled Exponential Growth and Decay. The first thing I'd like you to do is to take a look at the first three problems and sketch what you think those graphs look like. Now remember, you can always use a table of values to approximate what you think the graph would look like. Pause here and if necessary, plug in some values, easy values, that might help you to sketch these graphs. The first graph you should know is a line. This is right through the origin, and it's basically evenly sloped upwards. Y equals x. The second graph is a parabola, and it's your most basic parabola, y equals x squared. The third is your exponential function. And if you didn't know, you could have plugged in some values for x and see what y equals. Well, if x is 0, y is going to be anything to the 0 power is 1. If x is 1, it's going to be 2. If x is 2, it's going to be 4. If x is negative 1, it's going to be 1/2. If x is negative 2, it's going to be 1/4, etc. This graph actually looks like this, and we call that exponential growth. An exponential function is of the form y equals a times b to the x power. So there might be a coefficient there and there might not. One thing you want to keep in mind, and it's down here, is remember your order of operations. So we're always taking that b to the x and then multiplying it by our coefficient. This is a new word for you. This word is asymptote, and an asymptote on a graph you'll become more familiar with in Algebra 2. It's a line that the graph approaches but never quite reaches or touches. So if you think about this graph here, it's never going to touch the x-axis. Y can never be 0. You're never going to get y to be 0 in that equation. If x is 0, obviously we had that y is 1. But you're never going to be able to have a value for x that's going to give you a value for y of 0. So the asymptote is the line y equals 0. Here they're going to tell you what they want your domain to be, and we are going to graph the functions. So the first thing you're going to do is create a table for x and y, and -2, -1, 0, 1, 2, 3, and 4. Try to find what y equals. If x is -2, y is 400. If x is -1, y is 200. If x is 0, we have 100. If x is 1, we have 50. X is 2, we have 25. Remember your order of operations. So I'm taking 0.5 to the second power, multiplying it by 100. Then if x is 3, it's 12.5, and if x is 4, it's 6.25. So obviously these aren't the nicest things in the world to graph, but we can graph them based on what we see here. One of the things we need to do is calibrate our y-axis a little differently. If I made each of these 50, -2, 400, -1, 200, 1, 50, 100, so this is 50, 2 is 25. You can see it gets really hard to graph. So at 3, I'm at 12.25 way down here. It's hard to do on the smartboard, but it's hard to do on regular graph paper as far as that goes. But it kind of goes like this, and that's going to be the graph of y equals 100 times 0.5 to the x. So knowing that, why don't you try the next one on your own? Pause it here and see what you can graph. I made a table, and my x and y values were -2.25, -1.5, 0 is 1, 1 is 2, 2 is 4, 3 is 8, and 4 is 16. I would graph those, and I get something like it crosses here, and 3, 8, so it really slopes up. Kind of like that. Okay, so hopefully yours is similar, and you don't need that one there if you're asking that question. If you look at b in each of these functions, we can make a connection to the value of b and whether the graph shows exponential growth and decay. In this case, a times b to the x. This isn't b like y-intercept. This is my a times b to the x. In this case, this is decay. And what do we see about this value? This value is less than 1. When b is less than 1, the graph descends, and it means we have exponential decay. When b is greater than 1, in the case of the second graph, this 2, this is exponential growth. And you'll notice that b is greater than 1, so we have an ascending graph, and that means exponential growth. So if we take a look at the next page, it gives us a general formula for growth and decay. A is the initial amount, R is the rate, and X is time. And you're going to see how this works. It looks very complicated, but I think with a few examples, you'll begin to understand. Notice that they're very similar formulas. Growth is a sum and decay is a difference. There are many real-world applications of growth and decay. The most commonly used are populations, bacteria growth, radioactive substances, temperature, credit payments, compound interest. We'll see a few problems as we go on. First of all, we want to guess the shape of the graph and then check it by graphing it on your calculator. And you can just use that exponent key, that little caret top thing. In the first one, that's going to be something times 4 to the x, well, that's going to be growth because that's a positive b. 1 times 4 to the x. And this one's 0.25 to the x, so that's a decay. And you could graph those on your calculator and you will see that this one is a high sloping line like that, and that's going to be, actually, I think it's even more severe than that graph. Figured I would show you a little bit. To graph this, you would just go into your graphing menu, and that's going to be f of x equals, and I could do, that one graph asked me to do 4 to the x, so that's going to be 4, and then you use this little caret top, and then x, enter. Okay, and that's what that graph's going to look like. Or I could go back, new document, add a graph, and in this case it's going to be 0.25 to the x, so 0.25 to the x, enter, and there's your graph. Okay, so for each example, determine if the graph will show growth or decay, and then give the percent of increase or decrease from the time period. If you look at those formulas up above, this is telling you that if you want to see the percent of increase, that's your rate. Look at the first example. It says y equals 4 times 1.2 to the x. Well, how can we put this in a format of y equals 4 times 1 plus or minus some number to the x? What is that going to be? This number is going to have to be 0.2, right? So that means a 20% increase. Make sense? Pretty intuitive, actually. So why don't you try the next 3 on your own and come back and check with me. Number 2, it's going to have to be, this number here is going to have to be 1 plus or minus something. Well, if I think about that, it would have to be 1 minus 0.75 to get 0.25, right? That's 75% decay. Number 3, 1/2. Well, that's the same thing as 8 times 0.5 to the x. 0.5 to the x would have to be a decay of 50%. 2 to the x would have to be 1 plus 1, or growth of 100%. Remember, we're in percents here. Hopefully, we can get a little practice done on this tomorrow. I would like you definitely to complete your tickets to come in, because I think there should be some questions on this, and then we're going to spend a couple days practicing. So have a great night, and I will see you tomorrow.